Question 1 says, to demonstrate the interference of light waves in 1805, Thomas Young allowed monochromatic light from an illuminated single slit to fall on a pair of narrow, closely spaced slits. Explain why it was necessary to use monochromatic light in part A, and B, explain why it was necessary to use a single slit before the double slit. So to a certain extent, the answer to both of these questions is because we need to achieve this coherence of the light that comes from the double slit. So firstly, why does it need to be monochromatic? So for interference pattern to remain stationary, I'm going to say, the path difference at any point on the screen must remain constant when measured in wavelengths. So what this is getting at is, if we imagine our two slits, we've got light going off from the pair of them, and we know we draw a little triangle in here and we find this small path difference. These two meet at the screen some long way away. This, whichever point on the screen we're looking at, up and down here, this has to be the same number of wavelengths every time. If we're talking about an interference maxima, it has to be a whole number of wavelengths. If we're talking about an interference minima, it has to be a number of half wavelengths, so an integer plus a half number of wavelengths. But at any point in between, it also has to be a set number of wavelengths, and it has to stay the same number of wavelengths as time progresses. Otherwise, the point that previously was an interference maxima, a short while later, might not be a maxima anymore, in which case we wouldn't get this stationary interference pattern on the screen. Second one, why is it necessary to use a single slit before a double slit? So the answer to a certain extent is because we need coherent light. What we might picture is, if you have light coming towards a single slit, the sort of GCSE version is we get these waves spreading out on the far side. But the problem that Thomas Young solved by using this single slit was these wave fronts that we're drawing here are effectively already what we'd say is spatially coherent, because all the way along this line the peaks are appearing in the same place. Now, for normal light, probably a better picture for the wave fronts, even when it's been through a monochromatic filter, is that the peaks don't appear in the same place as you go across the wave front from left to right. So what we end up at arriving at the slit is not these nice straight lines, but bits where a peak over here might arrive a bit before the peak next to it. These are parts of the same wave. We could almost picture them as entirely separate waves. You could picture as a whole set of wave fronts coming here and then different ones, same wavelength but not lined up with the first lot here, here and here. And our single slit does this job of selecting a small part of the wave front so that we can say the waves coming out this side are spatially coherent. So I think that's probably a good answer, to select a small part of the incoming wave front, so wave fronts become spatially coherent before arriving at the double slit. Oh, this doesn't say slit. There we are. So to a certain extent, as I say, the answer to both is to achieve coherence, so to make sure we've got coherent light, but that's kind of separating it out into two parts. C. Describe how the interference pattern is produced on the screen. You should mention the principle of superposition in your answer. So in terms of a diagram, we might want to switch to a ray diagram at this point. We've got rays, coming from both slits off at some angle. If this angle, I'm not going to mark it there, that's a bad choice. If this angle in here is theta, and the separation of these is a distance d, then we can mark on this extra really important triangle in here, with a right angle at this side. So the green lines after this have exactly the same length until they arrive at this point on the screen, but this in here is what we call the path difference. With a bit of trig, we can see its length is d sine theta from that little right angle triangle. This angle in here is also theta. So we can say at an angle theta, as long as it's not 0, there is a path difference between the two paths, the two rays perhaps we should say, that go to a single point on the screen. This introduces a phase difference the two rays will add together by superposition if n lambda is equal to d sine theta. In other words, if we have a whole number of wavelengths equal to the path difference, we get constructive interference and what we call a maxima.